good evening. Welcome back. Here we are in an amateur radio class. Ham radio, that's still going on, that old thing? Yeah, and it's still a heck of a lot of fun to be able to put together a radio station of your own and be able to talk locally or around the world independent of the internet or cell phones or other things as well. So if you just stumbled upon us on YouTube, well, stick around and hopefully we can get you excited. What we do here is prepare students to take their very first amateur radio exam. It's a 35-question multiple choice test that you can either take locally at a local amateur radio club, or there are online tests available as well. And we're here now to chapter 3 in this book. This is the, whoops, nope, not yet. Come back to me, please, thank you. We have new personnel in our control room, so it's going to be interesting tonight, but it's going to be great. So this is the book that we use. It's the American Radio Relay League's License Manual for the Technician Class, the 5th edition. So if you'd like to play along at home, this is the book we use. It has all of the test questions and all of the answers. They're not secret. They're all in the back of the book. The thing is that the order of the answers on your actual test are not going to be in the same order. So don't memorize A, B, C, or D. We tell you that. But we want you to know, number one, what's the right answer? And number two, why it's the right answer, because that suggests that we've given you some knowledge so that you're not going into this cold. So anyway, stick around. All right, now come back to the laptop. Here we are at chapter 3, electricity components and circuits, and we're going to start with electricity. And you know that we're here a maximum of 2 hours every Wednesday night, to teach electronics or electricity in just 2 hours is unbelievable. We're going to have to skim the surface. We're not going to go very far in depth, because you know that electronics semester-long, multi-semester-long, college-level courses. So anyway, don't be concerned if a lot of this goes, whoa, this is a lot of stuff. We're going to make sure that you get to know what you need to know, not only to become a great ham radio operator, but also to pass the test. So with electricity, the basics are an insulator versus a conductor. You don't have to, if you want to unmute yourself on Zoom, what are some good insulators to the flow of electrons? What do you think?
Metal.
So metal is a good conductor, but what about a good
glass?
Glass, yeah. Wood. Plastics. Yeah, so those are good insulators. Okay, good conductors. We've talked about metal. What kinds of metal?
Copper.
Copper is the number one we think of. What's a really good conductor?
Gold.
Gold is the best, and silver is a good conductor. So yeah, so we got it. Insulators are those things that prevent current flow of electricity, and the insulators you see here are actually built purposefully this way to improve their high voltage resistance so that you don't have arc-overs at the ends of antennas or on power lines. That's why they make them this way. And of course, conductors, metals, copper is the most common, aluminum wiring, sometimes they used to use those in house wiring, not so much anymore. So conductors and insulators to the flow of electricity. And electricity is the movement of an electrical charge through a conductor. And it's because metals have free electrons in the outer band of the atoms. And because of the free electrons, they can be urged or energized to move. And so here we're seeing the negative charged electrons moving from the left to the right. We could also say that a positive charge is moving from the right to the left. We're not going to go too deep into this, but know that there are two theories of current flow, and we use the conventional theory of current flow pretty much, which means that we say that current flows from positive to negative. So here we have an electric circuit, and let me turn on my laser pointer here. There we go. And note, we have a switch up here. This is a single pole, single throw switch. And when the switch is closed, now they're looking at electrons. So this is electron flow from the negative side of the battery through a lamp in this case, and back to the positive side of the battery. So this is electron current flow. Key concepts in electricity has to do with voltage, current, and resistance. Voltage is the pressure that is pushing the electrons through the conductors. Current is a counting of the electrons that are actually flowing. You're actually measuring the intensity of that current going through the wire. And resistance is the opposition to that current flow. Coming from voltage, current, and resistance, then we also can talk about power, the amount of energy that is consumed by a device. And power can be calculated by taking the voltage times the current and giving an answer in watts. So that's power. And a circuit is any path through which current can flow. Here's a pictorial that my colleague Dave Ivey found on the internet that kind of illustrates. There's Mr. Volt trying to push the current through a conductor, and Mr. Ohm there is trying to resist, trying to slow things down. So we have voltage, current, and resistance. And we say that voltage, we use the Ohm's law symbol E. It comes from the French electromotive force. So E is the symbol in Ohm's law for voltage, although when you're measuring it in volts, we use the letter V. This all means voltage. That's the pressure that triggers electron flow. Current, again from the French, I, intensity of current. So you'll see in the Ohm's law formula the letter I. But we measure current in amps or amperes. You'll also hear me say amperes because my old electronics instructor, Mr. Zielinski, always used to say amperes, and I got into that habit and I can't stop. Okay, and resistance, R, okay, that makes sense, is measured in ohms. So voltage is measured in volts, current is measured in amps, and resistance is measured in ohms. And we can also use the Greek letter omega. Over here, you see that right there? The last letter in the Greek alphabet is also a symbol for ohms. So you'll see that as well. Now, we're talking about voltage, the thing that pushes electrons through. There's direct current voltage, and there's alternating current voltage. So we're looking at here, and this is something that we'll look at graphs in various ways. We have amplitude on the vertical scale and time on the horizontal scale. And with DC voltage, the voltage doesn't change. In this case, it's positive with reference to ground, and it always stays positive. So a 12-volt car battery, for example, is always going to be in this orientation, always the same voltage all the time from that source. Whereas coming from your house outlet at home, that's alternating current. And what happens there is that over time, it may go negative, come back to zero, go back to a positive peak, come back to zero, negative peak over and over and over again. It's happening at 60 cycles per second in the United States, or 60 hertz. Alternating current, and this is what the waveform looks like. This is called a sine wave. All right, here's a trick question. Put on your thinking caps. Before I ask the question, though, let me just say that notice this goes negative and it goes positive. It goes negative and it goes positive. DC always stays on one side or the other, depending on the polarity. All right, with that information, is this an AC or a DC voltage?
DC.
DC.
It is what we would call pulsating DC. It's that sine wave we looked at there with half of it flipped over. And so this is pulsing in from 0 up to a positive value, back down to 0, pulsing back up again to a positive value, back down to 0. This is a waveform that is used in power supplies. When they take the AC that comes out of your wall, maybe through a transformer, goes down to a lower voltage, and then they rectify it and create this waveform in order to get DC out of AC. And schematically, if schematic diagrams are pictorials of how components are hooked up. And schematics, these are pretty simple, but for electronics devices that you use, for example, your televisions or radios or everything else, typically they have schematic diagrams of how everything is hooked up. So your ham radio transceiver probably has a service manual that has schematics for your radio. But here we have, very simple, this is the schematic symbol for a battery. We saw that earlier. They're showing the current flow. This is the schematic symbol for a resistor. So we know it has a resistance in ohms, and it's going back to the battery. Whereas here, this is an alternating current generator of some type. We don't know what type. And again, the current is flowing to the resistor in one direction, and then it alternates and goes back through the resistor in another direction over and over and over again. 60 cycles per second if we're talking about house current. And I mentioned car batteries. Car batteries are DC sources of energy, and they chemically store the DC energy. So I've been involved in electronics since high school. I graduated from high school in 1972, and then I got a chance to work in broadcasting in Michigan, and then I joined the Voice of America in 1988 and was sent overseas. My first overseas assignment was Liberia, West Africa. My second overseas assignment was in Munich, Germany. And so Ohm's law, the thing we're going to talk about here in just a little bit, it was ingrained in my brain. But I had no idea in Munich. Well, I was rushing to attend a meeting, I believe at the consulate in Munich, and I took a shortcut through a local cemetery. And as I was rounding a corner, I kind of tripped on the corner of a grave, and I looked down and looked over, and I was amazed because this is what I saw: the grave of George Simon Ohm, or Georg Simon Ohm, the guy, the German physicist who invented or came up with Ohm's law. And this is what his gravestone looks like. So it's kind of fascinating. Now, last week, if you remember, we used this pyramid to talk about the relationship between frequency and wavelength. And we said that the speed of light up here, we use the number 300, and the frequency in megahertz. If we knew these two, then we could calculate the wavelength, or 300 and the wavelength, we could calculate the frequency. Well, Ohm's law is very much like this. It's got its own pyramid. Remember I said E stands for voltage in Ohm's law. That's on the top. Current, the intensity of current, is here, and resistance is over here. So this is in volts, this is in amps, and this is in ohms. And what the purpose of these pyramids are is you put your thumb over the thing you're trying to determine, and it reminds you that the formula for resistance is E divided by I, or E over I. So here's a pictorial. The formula for current is E over R. The formula for voltage is I times R. So from this is the basis of Ohm's law. This relationship is a constant, and it exists in real life. Technicians all over the world use this relationship on a day-to-day, hourly, hour-by-hour basis. I mean, this can tell you a lot about a circuit. If you can measure the voltage across a known resistance, then you can calculate the current that is flowing through that. And that's sometimes important to know. So from Ohm's law, there's another similar pyramid. We call it Watt's law. It has to do with power. So power in watts is on the top. current in amps is on the bottom, and voltage in volts here is down below. Notice it spells pi. So I like this, like you to remember ear pi. I know it's hokey, but okay. Bad spelling of ear for Ohm's law and pi for Watt's law, and these relationships are important. Now we're not going to go into more complex, but from these relationships, I'm not going to scare you, but I just want you to know this exists. All of these formulas can be derived. So sometimes you might know power and you might know resistance, but you don't know current, so you can use one of the derivative formulas that you see here on this wheel. Okay, enough of that, don't want to scare you. So with a circuit, we've looked already at a series circuit. It's a circuit where we have a power source of some kind. In this case, it's a battery. It's going through a switch, and then it's going through the filament on one bulb here. It comes down, goes to the filament on another bulb, comes down, goes to the filament on another bulb here, comes down. This is your classic Christmas tree lights, where if one of the bulb burns out, current can't flow. The lights don't light up, because with a series circuit, current flows through each and every one of the components. And if one of them opens up, it's like an open switch, current can't flow through anything. Schematically, this would be illustrated as something like this, with here our battery power source and resistors in place of the lamps that we just looked at. So this is what we call a series circuit. Well, you know, if there's one, there's got to be something else, and the opposite, or the other circuit, is a parallel circuit. In this case, we have our power source on the pictorial, a battery, and it's connected to this lamp, but the wire continues to go through this lamp, and goes out and goes through this lamp. But notice in this case, if this lamp burns out, these two lamps will still be lit because they're directly connected back to the power source. There's nothing in series. So this is a parallel circuit, and this is the schematic of a parallel circuit, again, with the power source of the battery and resistors sitting in for the lamps. And technicians always are interested in what we call junctions, what's happening when two parts meet. So in this case, we have R1 in series with R2, and because it is a series circuit, we know that the current through this resistor is going to be equal to the current through this resistor, because it has to be. It's got to go through both of them at the same time. Whereas here, the current is going to divide up. So part of the current is going to go down through here, and part of the current is going to go down through here. And if these resistors are of equal value, the current will divide equally. So it'll be half current going through one resistor and half going through another. Voltage also behaves this way. If you've got a voltage coming in and you've got two resistors in series that are of equal value, let's say this is 10 volts coming in, and if they're of equal value, you'll have an output voltage here of 5 volts, half of the supply current. And you can calculate it using this formula down here. The voltage across parallel connected resistors is always going to be the same as the source. So in this case, our source is 12 volts. So the voltage across each resistor is going to be 12 volts, or 12 volts, or 12 volts, in this case, in a parallel circuit. All right, we talked about series circuit. We've talked about parallel circuit. Something you hear a lot about is a short circuit. I think my radio's not working. I've got a short circuit. What is a short circuit? Well, the normally operating circuit here is pretty simple. A battery, wire, going to a lamp, lighting the lamp. But if a wire falls across the lamp, all of the current is going to take the lowest resistance path, and a wire is very low resistance. So all of the current is going to flow this way, and none of it is going to reach the lamp. That's a short circuit. When there's some sort of current flow in a place where it shouldn't be flowing, that's a short circuit. A closed circuit is a normally operating circuit, on the left here. And an open circuit is when, say, a wire falls off and you have an opening. then current can't flow across that opening. So we have a short circuit, a closed circuit, and an open circuit. And you may have seen me there saying voltage across this and current through that. We determine the values of that using meters. Meters display amplitude of something, of voltage or current or whatever, on a numbered scale. And they can be an analog meter, as you see on the left there with a mirrored dial, or it can be a digital readout, as you see there on the right-hand side. And when you're connecting meters into a circuit, voltmeters connect in parallel with the device under test. So here's a voltmeter, and you see we want to measure the voltage across the lamp, so we're measuring in parallel with the device. So voltmeters are connected in parallel. Ammeters, because I mentioned earlier, they're kind of like they're counting electrons. I think of it like a turnstile at an old baseball stadium where people will go through and go click and click and click and click, counting people coming in. So that's what an ammeter is doing. It's counting electrons, click, 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 click. But you have to break the circuit and put the ammeter in series. So the whole point of this is ammeters are connected in series to make measurements. Voltmeters are connected in parallel. And one of the very first pieces of test equipment that you're likely going to buy that you'd find very valuable, and you can find them at Lowe's and Home Depot and other outlets, are multimeters. Multimeters are things that can measure current, can measure voltage, can measure resistance. In this case, the analog meter on the left, it's got a big knob here that you can adjust and switch to what range you want to be measuring. And this is an inexpensive digital voltmeter like you might find at Harbor Freight or someplace like that. All right, come back to me just for a second, Marion. So I want to let you in on a big secret. All right, you've been with me long enough, I think I can reveal this to you. Everything in electronics runs on smoke. Yeah, smoke. Come on back to the laptop. That's the big secret. We don't want to let the smoke out. When you see electronics fail, usually you'll see some smoke coming out, especially with your multimeter. And this is going to happen, unfortunately, it happens to everybody. But the multimeter that has this switch arrangement here, if you put it on the ohms scale to measure resistance, and you forget to move it to the voltage scale, and you have a piece of equipment, a radio or whatever, that's plugged in and turned on, and you want to make a voltage measurement, you have to do it that way. And you put your probes across whatever you're measuring, and the smoke comes out of your meter. And your meter doesn't work anymore, because remember, everything works on smoke. So don't do that, because you'll burn the voltage divider resistors that are inside the ohm meter. So just keep that secret in mind. Don't tell anybody. If you're going to be measuring high voltages, linear amplifiers, some tube-type transceivers, you're going to want to get something that's appropriate. You're going to want to get a multimeter that is rated to measure the voltage that's involved, and you may want to get a special probe like this for high voltage measurements. The quality of the meter and the quality of the probe really impact your safety. Note here we've got the guard here so that your hand can't slip down, and you've got these insulating things here so that high voltage can't jump to get you. So always keep that in mind, the quality of the meter and the quality of the probes, especially if you're working on high voltage equipment. All right, the next one is kind of a strange one, but they have it here in this section. If you're measuring a circuit that has a capacitor inside of it with an ohm meter, this is something that people will do is they'll make resistance checks in an unpowered radio, because you don't want to make a resistance measurement with a powered radio or you let the smoke out. But when you're testing in this manner, you may find that as you put your probe on a thing, you have very low resistance, and then it starts climbing back up again. This low resistance and climbing back up again is an indicator that there is a capacitor in the circuit, and what you're doing is you're charging the capacitor with your multimeter. All right, so right now what I'd like to do is move over to the smart board and have us do some practice problems with Ohm's law. So let me meander on over here. Grab my magic pen. Practice problems. Follow along, let's see how we're going to do it here. So the question we have is how much power is delivered to a circuit with 13.8 volts DC and 10 amps. So we're looking for power. That's what we want to know. So that tells me we're going to use that pi formula. So I can draw it up here. P I E. Yeah, you can take the smart board full if you want. So PIE, that's our power formula, so that's what we're looking for, and we know that power, if I cover up the P is equal to I times E. So in this case, I is 10 amps, E is 13.8, so 10 times 13.8 is going to give us 138, and the answer of power is going to be in watts. So I contend that the answer is going to be 138 watts. I think I have the answer next. Oh, here's our pi. I forgot I put it together this way. All right, and it is 138 watts. Finally, we get there. All right, let's try another. How much power is delivered to a circuit with 12 volts DC and 2.5 amps? So again, it's a power question. So we're going to use the pi pyramid that we looked at. And so we know that power is equal to I times E. I and E. So 2.5 amps times 12 volts equals 30 watts. And you can use a calculator, but that was not so difficult to know. So again, we're using that pi. There's the question. I forgot how I formulated these things. But yep, 30 watts. That's what we want. All right, let's keep going. How much current is required to deliver 120 watts at 12 volts DC? So again, it's the pi pyramid, but we're not looking for power, we have power. And we're not looking for voltage, we have voltage. What we're looking for is current. And if we use that, we know that I, that pyramid, is equal to P over E. So 120 divided by 12 is going to be 10 amps. Yep, we used the pi. That was our question. 10 amps. Indeed, we did it. All right, let's keep going. What is the resistance of a circuit in which a current of 3 amps flows when connected to 90 volts? Okay, there's no power in this one. So this must be Ohm's law. And remember the Ohm's law pyramid? E over I R. So we know I, and we know voltage. What we're looking for is resistance. So resistance from this is equal to E divided by I, or it's equal to 90 divided by 3. So in this case, the resistance, that's what we're looking for, has got to be equal to 90 divided by 3, or 30 ohms. There's Ohm's law. That was our question. Hey, we got it right. All right, let's keep going. What is the resistance of a circuit for which the applied voltage is 12 volts and the current flow is 1.5 amps? Again, this is Ohm's law. So I'm going to use what I did. Here's the Ohm's law formula. And we're looking for the resistance. So we know that R is equal to E, E's always on top, divided by I, which in this case is equal to 12 divided by 1.5, which is going to be equal to 8, and we'll use the omega, 8 ohms. The resistance is going to be equal to 8 ohms. Hey, we're smoking. Are you seeing how these are being used? These are relatively simple, but these are actual calculations that technicians do every day. All right, let's see. I think we got something else now. So here's a reminder. Ear pi. These are very important. We want you to memorize them. We want you to know them. And one way that you can do that, come on back over to the pod if you would. I want to introduce a concept to you that we use in the general class and the extra class, and I haven't really enforced it so much in the technician class, but it's something called a memory dump sheet. And what is a memory dump sheet? It's something that you know that you want to remember. And it's something that you can try to memorize in your brain, and then when you get to your test session, you can sit down and they'll be giving you a piece of scrap paper, turn it over, and write down what it is you want to remember. And I'm going to suggest you remember ear, pi, and that frequency pyramid, 300 divided by frequency times wavelength. If you get these three in your head, you can handle all of the math questions that are going to be on the technician test. Speaking of questions, let's go ahead and see what we can do here with our first questions. And you can get me off of there. And here we are. So electrical current is measured in which of the following units? You can go ahead and unmute and let me know.
Delta.
Delta. Current is measured in amps or amperes. Or as my instructor Zelinsky said, amperes. Electrical power is measured in which of the following units? Power.
Bravo.
You hear that? Bravo. Yes, watts, indeed. And what is the name for the flow of electrons in an electric circuit?
D. Delta.
Current. You're doing great. And what are the units of electrical resistance?
Charlie.
I tripped over his grave in Munich. Georg Simon Ohm. And what is the electrical term for the force that causes electron flow? The force.
Alpha.
The voltage. May the force be with you. Electromotive force, EMF. So why are metals generally good conductors of electricity?
Baker.
Yeah, they have many free electrons in the outer ring of their atoms. And which of the following is a good electrical insulator?
Bravo.
Glass. And which of the following describes alternating current?
Charlie.
Alpha. Oh,
Charlie. It is Charlie.
Oh, positive and negative.
Positive and negative. Remember, if it goes between positive and zero, that's pulsating DC. All right, which term describes the rate at which electrical energy is used?
Charlie.
It's going to be Charlie.
Yeah, it's power, indeed. And what type of current flow is opposed by resistance? Read carefully.
Delta.
Yeah, all of these. Direct current, alternating current, and radio frequency currents are all opposed by resistance. And what is the formula used to calculate power in a DC circuit?
Alpha.
It comes from the pi.
Alpha.
Yep. Power equals
Alpha.
current times voltage, or P equals I times E. And how much power is delivered, all right, here's a question, with a voltage of 13.8 volts DC and a current of 10 amps? How much power?
Alpha.
138.
Yeah, we did it on the board there, 138. How much power is delivered by a voltage of 12 volts and a current of 2.5 amps?
Bravo.
Bravo.
12 times 2.5 gives us 30. And how much current is required to deliver 120 watts at a voltage of 10 volts DC?
Bravo.
We're calculating current, so we take the power and divide it by the voltage, and it is Bravo, 10 amps.
Bravo. Yeah.
Yeah. All right, what formula is used to calculate current in a circuit?
Beta. Bravo.
Yeah, this is from Ohm's law. I equals E divided by R. And what formula is used to calculate voltage in a circuit?
Alpha.
Alpha.
Again, this is Ohm's law. E equals I times R. And what formula is used to calculate resistance in a circuit?
Bravo.
Bravo.
R equals E divided by I. Very good. And what is the resistance of a circuit in which a current of 3 amps flows when connected to 90 volts? So R equals E divided by I,
Bravo.
30 ohms. The answer is in ohms. 90 divided by 3. And what is the resistance of a circuit for which the applied voltage is 12 volts and the current flow is 1.5 amps?
Charlie.
So R equals E divided by I, 8 ohms. Charlie is correct. And what is the resistance of a circuit that draws 4 amps from a 12 volt source? R equals E divided by I,
Alpha.
3 ohms. Very good. And what is the current in a circuit with the applied voltage of 120 volts and a resistance of 80 ohms?
Delta.
120 divided by 80 gives you 1.5. And the answer is amps, 1.5 amps. Okay, what is the current through a 100 ohm resistor connected across 200 volts?
Charlie.
Ohm's law, I equals E divided by R. 200 divided by 100 is 2. Charlie is right. And what is the current through a 24 ohm resistor connected across 240 volts?
Charlie.
We see that? I equals E divided by R. 240 divided by 24 is 10 amps. And what is the voltage across a 2 ohm resistor if a current of 0.5 amps flows through it?
Alpha.
E equals I times R, so 0.5 times 2 is 1 volt.
1.
And what is the voltage across a 10 ohm resistor if a current of 1 amp flows through it?
Bravo.
E equals I times R, or 10 times 1, 10. And what is the voltage across a 10 ohm resistor if a current of 2 amps flows through it?
Delta.
Yep, twice that, 20 volts. And in which type of circuit is DC current the same through all components?
Yes.
In which,
Bravo.
In which type of circuit is current the same through all components? Could be AC, could be DC.
Alpha.
It's a series circuit.
Series.
Right. Current is the same. And in which type of circuit is the voltage the same across all components?
Bravo.
Yeah, that's parallel. Bravo. Yeah. And which instrument would you use to measure electric potential, also known as EMF, also known as
A voltmeter.
the letter
Alpha.
E?
Bravo.
Bravo. It's a voltmeter. You're measuring the electric potential, which is a pressure. And how is a voltmeter connected to a component to measure applied voltage?
B.
Alpha.
Bravo.
Bra.
Bravo.
B.
If you're measuring voltage, it's in parallel with the device under test. Remember, ammeters have to be the turnstile, and they would have to be in series. Well, that may be the next question. So when configured to measure current, how is a multimeter connected
Yeah.
to a component? Yeah, here we go.
In series.
In series, alpha, yeah. And which instrument is used to measure electric current?
Delta.
An ammeter measuring amps, yep. And which of the following can damage a multimeter?
Alpha.
Not alpha.
Oh. Charlie.
Attempting to measure voltage when you have it set for resistance and you let the smoke out. Which of the following measurements are made using a multimeter? Charlie, voltage and resistance, both of those could be measured using a multimeter. Impedance and reactance, no. Signal strength and noise, no. So what reading indicates that an ohm meter is connected across a large discharged capacitor?
Alpha.
Alpha.
Yeah, that's
Alpha.
that increasing resistance over time as you're charging the capacitor up. And which of the following precautions should be taken when measuring in-circuit resistance with an ohm meter?
Alpha.
Not alpha.
Bravo.
Bravo.
Yeah, you got to make sure that the circuit is not powered or you let the smoke out. So which of the following precautions should be taken when measuring high voltages?
Bravo.
Yeah, ensure that the voltmeter and the leads are rated for use at those voltages. And that, ladies and gentlemen, is the end of section 3.1. What we're going to do now is we're going to take 5 minutes. I want you to get up and move around and stretch and come back, and then we'll complete the rest of chapter 3. And we are back, and we had a very good question during the intermission, and I wanted to re-emphasize it, that here in our class, we're essentially producing a TV program. So we kind of move right along when we get to the questions and have you do the answers. But when you're actually sitting down to take your 35-question multiple choice test, in most cases, there is no time limit. In some of the European countries, I think in England, there is a time limit, but as long as the volunteer examiners are willing, they will sit with you and be patient and let you go over, at your own pace, the questions and answers. And it is always good to make sure you read the question very carefully and then read the answers very carefully. We want it to become almost automatic for you so that you know the question, you know the answer. But on the other hand, it can trip you up if you don't pay attention. Units, kilohertz versus megahertz, kilo ohms versus ohms. The number might be right, but the unit might be wrong. So yeah, it's very good. But you have as much time as you need. If you're going to be taking a test online for online sessions, I've never done that. I don't know what their requirements are there. They may have a time limit, I don't know. But for in-person sessions, generally not, because they're giving all classes of license tests, and the extra class has 50 questions. So they're going to be waiting around for them as well. So don't feel pressured as far as time. All right, let's get going on section 3.2, which is components and units. And inside of every piece of electronics that you've got, whether it be your small cell phone or big large screen TV, these are the components that are inside, or your transceiver for amateur radio. We're going to start out with, you recognize this symbol from what we talked about before, a resistance, or the devices themselves are called resistors. And the classic resistor looks something like this. It comes in a round tubular shape, and it may be made of carbon or maybe a wire-wound metal, maybe other different things. And there's usually a color band system on it. There's a color code, and if you know the color code, you can read the value and the tolerance of the resistor. So you can look at it and go, oh yeah, this is a 1.2 kilo ohm resistor with 20% tolerance. So resistors, they oppose current flow in a DC circuit. That's the definition for this section. And they're measured in ohms or kilo ohms or mega ohms. Resistors. They oppose DC current flow, and you think, well, of course, voltage and current across and through the resistor are in phase. What do you mean? Well, if the voltage across the resistor is going up, the current through the resistor will go up at exactly the same time. Well, Gary, isn't that always true? No, we're going to get to some other components where that's not true, and that's where the magic begins. But okay. Opposing current flow and voltage and current are in phase. And you can have variable resistors. Here's one on the left, commonly known as a volume control, also known as a potentiometer. And it's measured in ohms, and it's used for adjustments. And schematically, it can be written in one of two ways. This type here, which is just a simple line through, although it may be a three-terminal device. Or here's the three terminals. Variable resistors, potentiometers. All right, so that's resistors. Capacitors. Capacitors are made of two or more conductive surfaces separated by an insulator. Come back to me just for a second, if you would, Marion. So this is what I always do. Capacitors are two different plates of metal that are brought close to each other, but they're separated by an insulating material. It could be air, it could be plastic, it could be paper, it could be a layer of oxide material. It's very, very thin, but it keeps the metal plates separated. The metal plates could be just like you see here, or it could be like a long strip that is, a jelly roll that is wound around like a jelly roll to put into a small compact area a large surface area. Those are capacitors. So capacitors are made of two or more conductive surfaces separated by an insulating material. Capacitance is measured in the unit farads. And milli, micro, nano, and pico are prefixes used before farads for the most commonly seen capacitors. So you might have a 1 microfarad capacitor or a 360 picofarad capacitor. And here are the schematic diagrams. Here's a fixed capacitor. Here is a polarized capacitor. You need to put it in the circuit only one way. If it's an electrolytic power capacitor and you put it in the wrong way, it might explode on you and make a big mess, so you don't want that. And variable capacitors, which are used for tuning. Fixed capacitors with the through-hole design kind of look like this. And the bigger capacitors up here are electrolytics. This might be 470 microfarads or something like that. The really small ones are probably in the picofarad range. You get all sorts of different kinds of materials. Now, back in the day, I graduated from high school in 1972, and that's when I got most of my electronics training. It was physically impossible to buy a 1 farad capacitor. They didn't exist. The technology wasn't there. But now you or I can go to Mauser Electronics and buy one of these. Here is a 3,000 farad capacitor. It's only rated at 2.7 volts, but they make them now. They're called supercapacitors. So just wanted you to know a little bit of the history. Most of the time in radio, we're still dealing with the smaller values, but these larger values now do exist. Supercapacitors are used commonly, well, you may not like it. I don't know how loud you like your music in your car. But for the systems, the big power systems that they put in cars that shake the car, they've probably got one or more of the supercapacitors that are stabilizing the DC voltage going to the amplifiers. That's where they're commonly used. Variable capacitors, I mentioned that you can have these. These are tuning capacitors. They have a series of plates that are stationary. They're called stators. And you have a series of plates that rotate into the stator's rotor. And with this, you can vary the capacitance. These are in the hundreds of picofarad range, typical for these capacitors. So capacitors block DC current flow. That's their claim to fame. Capacitors resist AC current flow by storing energy in an electric field. Come back to me just for a second. Can you make me bigger? Thank you. With the plates, when DC current is applied to one of the plates, which one am I going to do? Okay, this one. Electrons build up on that plate and are repelled away from the other plate. And so while that is going on, briefly some current will flow, but then you have a static charge held there. And so we say that capacitors store energy in a static field or an electric field. Okay, back to the laptop. So capacitors resist AC current flow, storing energy in an electric field. Their ability to resist AC current flow is called capacitive reactance. And this capacitive reactance is measured in ohms. We use the same unit, but it's not exactly the same thing as ohms in a resistor, but it's very similar. So here's a capacitive reactance. We have that current flow. So on the one half of the AC cycle, current is flowing in this direction, building electrons on this plate. Electrons are leaving this plate and going back. And then on the other cycle, half of the cycle, it does the opposite. Electrons build up down here, absence of electrons go there. So this is a capacitive reactance that opposes AC current. And here, voltage and current at the capacitor are out of phase due to the creation of that electric field. It takes some time to build that field. So with capacitors, we say that current leads voltage. you'll have high current flow into the capacitor before the voltage will build up. That's a capacitor. An inductor, this just looks like wound pieces of wire. Well, that's exactly what it is. Inductors are like this, although you can have them look like this as well, where they can wind the wire around other materials that enhance its ability to store energy. And inductors, the schematic symbol here, L is the symbol for an inductor. So here's one inductor, here's two inductors, here's three inductors. Are these inductors in series or in parallel? What do you think? Everybody's shy.
Parallel.
Yeah, they're in parallel. Very good. Thank you so much.
Parallel.
All right. So when in the 1970s, it was possible to build a 1 Henry coil. The Henry is the unit of inductance, named after this gentleman. So you can build a 1 Henry coil, although millihenry is a typical value for radio frequency chokes and other inductors. So inductance is measured in henries. Remember, capacitance is measured in farads. Inductance is measured in henries. Inductors pass DC current flow. Remember, capacitors block DC current flow, but inductors are just wire, so they pass DC current flow. And inductors resist AC current flow, storing energy in a magnetic field. That coil of wire is an electromagnet. And so as energy is applied to the inductor, you're building up a magnetic field. Resisting the AC current flow is called inductive reactance, and reactance, much like capacitive reactance, is also measured in ohms. So some key points to remember is that it opposes AC current flow, and voltage and current at the inductor are out of phase with each other due to the creation of the magnetic field. And it's just the opposite of a capacitor. We say with an inductor, the voltage comes up first before the current is able to go through because of the building of the magnetic field. Now, I said you can build the inductors by wrapping them around other materials. Well, if you have two inductors wound around the same material, you can create something called a transformer. And a transformer is used with AC power. And so here we have what we call the primary, where AC power is being fed in. Notice there's a large number of turns over here. Over here we have fewer number of turns. This is the secondary. And this would be what we would call a step-down transformer, transforming, say, 120 volts coming in over here down to something like maybe 24 volts coming out over here. Schematically, this is what it would look like. Here's the step-down transformer. More windings here on the left, fewer on the secondary here on the right. We've got a plug. We've got our single-pole, single-throw switch. We've got a fuse that is for overcurrent protection. So these are the things we want you to know about resistors, capacitors, and inductors. Now there's one other concept that I'm just going to throw in here briefly. You don't have to fully understand it yet in the technician class, but you'll hear this bandied about, so I want you to know, and that's impedance. Impedance is the opposition to AC current flow caused by the combination of resistance and reactance. And that reactance could be either inductive reactance or capacitive reactance. And for impedance, the unit of measure is the ohm. You've heard that already. Resistors measured in ohms. Capacitive reactance, ohms. Inductive reactance, ohms. Well, now here's another one, impedance, also measured in ohms. I don't know if you've been involved in hooking up a stereo system. I don't know if that's a thing that people do anymore, or in your car or whatnot, and you buy speakers, and the speakers are rated at 8 ohms or 4 ohms. That's an impedance, and it's the combination of the inductive reactance of the wire that's in the speaker for the voice coil and the resistance of the wire. And the two of them combine to make either an 8 ohm impedance speaker or a 4 ohm speaker. The standard output impedance of a ham radio transceiver is 50 ohms. That's an impedance value. We say that the coax cable has a characteristic impedance. You'll be hearing more about that as we come up. Now, I've shown you the single pole, single throw switch in a couple of our schematics earlier. There are other types of switches. Down below, there's the single pole double throw, which is where you can take one circuit and switch it between one or the other of a circuit. There are other switch types as well, the double pole single throw and the granddaddy, the double pole double throw. But just know about those, but specifically know about the single pole double throw because that might be on a test question. And in some units, you need to have a relay. A relay is an electrically controlled switch. And so you apply voltage to a coil here, which becomes an electromagnet. It pulls in this lever arm here and mechanically closes a switch up here. So this is a relay, and it's something that can be controlled remotely. This is what they look like in PC boards or inserts in a lot of equipment in industry, relays. We saw the fuse earlier, and I commented that it's for overcurrent protection. Both fuses and circuit breakers, for AC circuits we primarily use circuit breakers now, they're designed to open if the current is too much, if it's beyond the rating of the device. So if you've got a 5 amp fuse, it should blow if you've got 5 amps and more. At that point it should open up. Or the circuit breaker, if it's a 15 amp circuit breaker, it should trip if you draw more than 15 amps. Again, we're covering a lot of ground here, which we would go in depth in college classes, but we're not able to do that here. Remember, this is a licensing class, not an electronics class. Semiconductors, hokey smokes. All right, we're going to talk just briefly about semiconductors. The most basic type of semiconductor is a diode. A diode allows DC current to flow only in one direction. So in this case, if you applied a positive voltage to the anode of this device, current would flow out the cathode and on to the rest of the circuit. But if you applied a positive voltage over here, it would be blocked by the diode. So only in one direction. This is the schematic symbol for a diode, and this is what one physically looks like. And the cathode, or the output line here of a positive voltage, is always marked with a stripe on the diode. And there are different kinds of diodes. This is a power diode that would probably be used in a power supply, in a rectifier circuit to take AC down to pulsating DC. But you can also have smaller signal diodes. These are made out of germanium, a semiconductor, while these are made out of silicon, another semiconductor. Germanium diodes have a DC drop of voltage across them when they conduct of 0.2 volts, whereas silicon diodes have a DC voltage drop across them when they conduct of 0.7 volts. So that's a way to tell if a diode is actually operating properly, is to take your voltmeter on the volts range and measure across the diodes and see, is it 0.7 or is it 0.2, is it some other value? If it's some other value, the diode is probably bad. And diodes are used in this case, this is called a full wave bridge rectifier, where we have AC voltage coming in here. This is probably from a step-down transformer that we saw earlier. And this converts the AC signal into pulsating DC, like we saw over there in the earlier diagram. And pulsating DC in this case is being applied directly to a load. Most of the time, however, you'll have a regulated power supply where we will have our rectifier here. Then we'll have filter capacitors, which take this pulsating DC and smooths it out. So it's more like a DC, pure DC, but then it goes into a voltage regulator, which converts it into pure DC. This is the kind of power supply that you would probably buy to power your ham radio equipment in your ham shack, if it's a 12-volt equipment. We saw lamps, bulbs earlier, but they've largely been replaced now in modern equipment as an indicator with LEDs, or light-emitting diodes. current through a light-emitting diode when it's forward biased, positive voltage going through the diode and on back to the source, will emit photons. It emits light. And they can be designed in different color ranges, green, blue, red, etc. Also, with LEDs, there's always this current limiting resistor, typically about 100 ohms. And if you don't have this, the LEDs will typically burn out almost immediately. So if you're going to use LEDs, you always have to have a current limiting resistor. And this is what they physically look like. You probably have seen them. Moving right along, transistors. I was very fortunate in 1972. It was the transition time between vacuum tubes and solid-state devices. And so I got instruction in both camps. But it was a really new big thing, transistors and solid-state devices. The name transistor is derived from transfer resistor. And its characteristic is that an input voltage or current, a small input voltage or current, is used to control a larger output voltage or current. And that small signal at the input, then you can either use it in two ways, can be amplified to a larger signal at the output. So that's using a transistor as an amplifier. A transistor can also be used as a switch, where a small signal at the input turns on or off current flow at the output. So transistors can be used as amplifiers or switches. Transistors have gain. That's the characteristic that allows it to amplify. And bipolar transistors are made up of 3 layers of specially prepared semiconductor material. N-type material, P-type material, N-type material, or P-type material, N-type material, P-type material. PNP, this is a PNP transistor, or NPN, NPN-type transistor. And transistors have 3 legs: base, collector, and emitter, or emitter, base, and collector if you go in the order up here. Typically the base is the input, although they can be configured in different ways. And bipolar transistors, they were the first types of transistors to be introduced. Nowadays they look something like this, although in integrated circuits you can have hundreds, if not thousands, if not millions of transistors, in one chip. It's gotten that good. But discrete transistors, this is what they look like. And in a schematic diagram, here's a bipolar transistor. Again, we have the base, emitter, and collector, the 3 leads. We have an input voltage at a fairly low voltage. It's coming in here. What is this? What is this device right here? What do you think? If you're on Zoom, go ahead and unmute. What do you think?
Capacitor.
It is a capacitor. Very good. All right. And so it's passing the AC but blocking DC. That's what a capacitor does. Okay, here we have, what are these?
Resistor.
Those are resistors, and they're being used as a voltage divider like we saw earlier. So it sets a voltage at this point. That low AC signal is allowed to come in, and it comes out on the collector side through, again, what is it, another capacitor, and comes out here. And notice the output voltage over here is 2.5 volts peak to peak, much larger than over here. So this transistor has gain. Also note something else. Here it went positive, then negative. Over here it goes negative, then positive. This is an inverting amplifier. It has gain, but it actually inverts the phase of the signal. That's how it works. So this is a transistor in a gain amplifier. Now, bipolar transistors were the first, but later they came along with field effect transistors. Again, there are 3 terminals, the source, gate, and drain. The gate is typically the input to this, and you can have N-channel FETs and P-channel FETs, much like with the NPN and PNP. And they're built somewhat differently, where you have, in this case, a P material down here, and you have a controlling gate over here. There are different kinds of field effect transistors. We're not going to go into that in this class, but in further classes, general and extra, yeah, we do. We talk a lot more about the different kinds of field effect transistors. And in a schematic, this is a schematic diagram of a field effect transistor surrounded by bipolar transistors. And I mentioned integrated circuits. Integrated circuits incorporate hundreds, if not thousands, of these devices into one device. Or they can be simpler. They can be digital logic gates that hundreds of transistors are used for digital logic. So we talked about earlier the capacitors and the inductors. And I told you that the voltage and the current in those devices are not in phase all the time. There's a special case when you put a capacitor and an inductor either in series with each other on the left or in parallel with each other on the right, and it's at a frequency where the capacitive reactance is equal to, in value, the inductive reactance. When that happens, that is called a resonant circuit. And what happens in a series resonant circuit, like you see over here, is at that frequency where the reactances of each are the same. They're the same, but they're out of phase, and it becomes a short circuit. This is a tuned circuit. It allows us to tune for a particular frequency. So we're not going to go deep into resonant circuits in the technician class, but it's the basis of how you can tune a radio. It's a resonant circuit. Same thing goes with a parallel resonant circuit, where if the reactance of the capacitor is equal to the reactance of the inductor at a particular frequency, then it's resonant at that frequency. And what happens is the energy between the two devices go back and forth and back and forth. And if there wasn't for resistance in the circuit, it would do this forever. And a parallel resonant circuit at resonance becomes an open circuit. So resonant circuits, just be aware that they exist. And it's a fascinating part that we'll talk more about in the general class and the amateur extra class. We do want you to upgrade. And again, we talked about impedance earlier as the combination of a reactance and a resistance, and just want you to know that impedance can be expressed using polar or vector coordinates. So here's resistance on this graph, here is inductive reactance on this graph, and the magnitude of the impedance is actually this line here. All right, that's way more than you need to know for the technician, but it's coming. So resistance, as a review, measured in ohms, capacitive reactance measured in ohms, inductive reactance measured in ohms, and impedance is also measured in ohms. And they're similar but different. And the definitions are that resistance has opposition to DC current flow, whereas impedance is opposition to AC current flow by definition for this section. So just keep that in mind. All right, some questions. What describes the ability to store energy in an electric field?
Delta.
E.
That is capacitance. You caught me taking a drink of water there. Yeah, okay. And what is the unit of capacitance?
Phase.
The farad.
Farad.
Back in the 70s, you couldn't build a 1 farad capacitor, but now you can. And what describes the ability to store energy in a magnetic field?
Delta.
See that? Yeah, the inductor, the inductance stores energy in a magnetic field. And what is the unit of inductance?
Charlie.
Yeah, I used to have an Uncle Henry, so I always think of him. And what is the unit of impedance?
Delta.
It's one of those ohms, yeah. And what is impedance by definition?
Alpha.
It is the opposition to AC current flow. And what electrical component opposes the flow of current in a DC circuit?
Alpha.
By definition, yeah, a resistor. Now, earlier on, we told you that the resistor will oppose AC current flow, DC current flow, RF current. Now here they're wanting to change the game. I don't know why they did that, but okay. What type of component is often used as an adjustable volume control?
Charlie.
That's the potentiometer. And what electrical parameter is controlled by a potentiometer?
Capacitance.
No.
Bravo.
Resistance.
It's also known as a variable resistor. So,
Resistor.
yeah, potentiometer or variable resistor changes resistance. And what electrical component stores energy in an electric field?
Bravo.
That's a capacitor. And what type of electrical component consists of conductive surfaces separated by an insulator?
Delta.
Yeah, that also is a capacitor. And what type of electrical component stores energy in a magnetic field?
Bravo.
Charlie.
Charlie, that's an inductor, the electromagnet. And what electrical component is typically constructed as a coil of wire?
Delta.
Also the electromagnet, the inductor, yeah. And what is the function of an SPDT switch?
Charlie.
Yeah,
Charlie.
single circuit, you can switch it between one of two other circuits. And what electrical component is used to protect other circuit components from current overloads?
Alpha.
That's a fuse. All right, look closely here. Put your glasses on. What type of switch is represented by component 3 in this figure?
Alpha.
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 We say alpha, that's single pole, single throw switch. If you have a handicap, or I hate to say it that way, but if you have a visual impairment, you can request of your volunteer examiner team to have an exam without pictorials, because we know it can be difficult to see, so just keep that in mind. So which is true about forward voltage drop in a diode?
Alpha.
Remember, I showed you the germanium and then I showed you the silicon. Germanium voltage drop is 0.2 volts, germanium is 0.7, so it is lower in some diode types than in others. And what electronic component allows current to flow in only one direction?
Charlie.
That's a diode. And which of these components can be used as an electronic switch?
Bravo.
Not Bravo.
Charlie.
Charlie, a transistor can be used as a switch or an amplifier. And which of the following components consist of 3 regions of semiconductor material?
Bravo.
Transistor.
Yeah,
Bravo.
that's a transistor, an NPN or a PNP. Yep. And what type of transistor has a gate, drain, and a source?
Bravo.
That's a field effect transistor, another type of transistor. They have different characteristics, but we won't go into that for this class. So how is the cathode lead on a semiconductor diode often marked on the package? That's that stripe at the one end of that device, yeah. And what causes a light-emitting diode to emit light? When does it light up?
Alpha.
When it has forward current, when it's conducting. And what does the abbreviation FET stand for?
Delta.
Delta Field Effect Transistor. Very good. And what are the names for the electrodes of a diode? You remember?
Charlie.
It comes from vacuum tubes, anode and cathode. And which of the following can provide power gain?
Alpha.
Not alpha.
Bravo.
Yep, transistors. Transistors have the characteristic of gain when they're used as an amplifier. Transformers can transform voltages, but they don't increase power. All right, what is the term that describes a device's ability to amplify a signal? Oh, we just talked about it.
Alpha.
Gain, yes. And what are the names of the electrodes of a bipolar junction transistor?
Bravo.
Emitter, base, and collector. And what is the name of an electrical wiring diagram that uses standard component symbols?
Charlie.
That's a schematic. All right, another diagram here. What is the component number 1 in this figure?
Resistor.
Alpha.
That's a resistor, yes indeed. And what is component number 2?
Transistor.
Can't see it. It's
Bravo.
It's this guy right here, yeah. That's a transistor. And what is component 3?
Oh, Charlie.
Charlie.
That's a lamp, it's up there, yes indeed. And number 4,
battery.
that's a battery, a delta, yes indeed. All right, another diagram. What is component 6?
Bravo.
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 That is a capacitor, indeed. And component number 8,
Variable.
Delta.
it's a diode, and it's a light emitting diode, because that's what the photons are coming off here. That's what this means here. That's a light emitting diode. All right. And what is component 9?
Variable resistor.
That's a variable resistor. It's a resistor, and it's got this wiper on it that varies. So yeah, it's a variable resistor. All right, and component 4,
Transform.
that's a transformer. And what is component 3?
Variable inductor.
Delta.
Yes, very good. We didn't talk about it specifically, but variable inductor, you got it. All right, and what is component 4?
Alpha.
Alpha.
That's an antenna. That's the schematic symbol for an antenna. And which of the following is accurately represented in electrical schematics?
Charlie.
Charlie.
The way the components are connected together, component connections. And which of the following devices or circuits changes an alternating current into varying direct current?
Rectifier.
Bravo.
That's a rectifier. We looked at the bridge rectifier there. And what is a relay?
Alpha.
Alpha.
It's an electronically controlled switch. Whoops, that jumped. Okay, sorry about that. And which of the following displays an electrical quantity as a numeric value?
Charlie.
Charlie.
That's a meter. Could be analog, could be digital. And what component changes 120 volts AC power to a lower AC voltage for other uses?
Bravo.
That's a transformer, step-down transformer. And which of the following is commonly used as a visual indicator?
Alpha.
Light-emitting diodes, LEDs. And which of the following is combined with an inductor to make a resonant circuit? You have an inductor and a delta capacitor. Inductors and capacitors together make resonant circuits. And what is the name of a device that combines several semiconductors and other components into one package?
Charlie.
That's an integrated circuit. All right, back to the schematics. What is the function of component 2 in this figure? What is its function?
Charlie.
Bravo.
Charlie.
Charlie.
It is Charlie. You're using a transistor in this case as a switch. It's to control the flow of current. Small voltage on the input there will allow a greater current to flow on the output. And which of the following is a resonant or tuned circuit?
Alpha.
The two things you have to have are an inductor and a capacitor, and they could be connected in either series or parallel. And what is the purpose of a fuse?
Bravo.
Yep, to remove power in case of an overload. And why should a 5 amp fuse never be replaced with a 20 amp fuse?
Charlie.
Charlie.
Excessive current could cause a fire and let the smoke out. Yeah, okay. Last section, radio circuits. So you've probably all been to a basketball game. This is what I remember in high school. And the PA guy is on the system and he's announcing and whatnot. And somebody turns the gain up too far and it starts howling. And, you know, the big, you cover your ears because it's howling. That's audio feedback. That's the output of the speaker is coming back into the microphone and being amplified again and back and again. This feedback is also known as an oscillation. And oscillators are circuits in radio. Oscillators specifically are taking an amplifier with gain, taking a portion of its output through a filter, a feedback circuit, so it filters to one frequency and goes back to the input of the amplifier, and this circuit then generates an AC waveform at one frequency. That's an oscillator. And an oscillator can have a feedback circuit consisting of capacitors and inductors, or in this case, the feedback circuit has a crystal. So this is a crystal-controlled oscillator using a transistor, an NPN transistor, and it's generating output on one frequency, the frequency to which the crystal is resonant. Back in the day, with novice amateur radio operators, they were required to use crystal-controlled transmitters. So this was something that was fairly common. We talked about filters in the case of feedback and generating oscillations and whatnot. Just in general, know that there are different kinds of filters: high pass, low pass, band pass. A simple circuit is just a capacitor in parallel going to ground, which takes out all of the high frequencies. Or if you put the capacitor in series, then it takes out all the low frequencies. So high pass filter, low pass filter, and if you look on a frequency chart, this is how they roll off. Low pass filter passes low frequencies, no problem, but blocks higher frequencies. High pass blocks lower frequencies and passes high frequencies. Used to be questions on the test about these. There aren't anymore, but I still think it's a good thing for you to know. So here's a transmitter diagram. This is for a CW transmitter, and I got a question earlier today. What is CW? It stands for continuous wave. Come back to me just for a second, Marion. So back in the day, you know, before there were vacuum tubes in wide use, radio operators, everybody was an amateur back then, used to generate signals using arcs. They'd spin up a generator to very high voltage, and they would, think of a Frankenstein movie, do a telegraph key, and it would arc when, you know, arc, and that arc, that lightning there would be sent off to a small filter circuit and then out to an antenna. That was a spark gap transmitter. That's why they used to call radio operators on board ships sparks, because they were literally transmitting with sparks. Well, later on, they came up with circuits and the ability to generate a very pure, continuous tone on one frequency. The sparking used a band of frequencies, but here, one frequency. So that's where the continuous comes in. Now, CW, we use as an abbreviation for transmitters that send and send Morse code. And so if you're starting and stopping it in a pattern, well, isn't that discontinuous? Okay, well, that's argumentative, but CW means Morse code. So here's a Morse code transmitter go back to the laptop if you would, with an oscillator, with an output on a particular frequency, a driver amplifier, and it goes out to a power amplifier, and your Morse code key is controlling both of these amplifier stages on and off, so that a pattern of radio frequency energy comes out from the transmitter using the Morse code to impose information on the radio frequency carrier. And putting information on the radio frequency carrier is called modulation. So in this case, they're modulating it by turning it on and off using a pattern that somebody else at the opposite end can recognize. Later on, they discovered, okay, we can modulate the radio frequency carrier with audio. And we can carry audio over radio frequency waves. And so here's the audio signal up here, this low frequency signal. Here's our radio frequency carrier at a much, much higher frequency, megahertz or something like that. And two types of modulation. One is amplitude modulation, where the amplitude of the radio frequency carrier is varied in step with the audio modulation. So it's, and we're looking here in the time domain, so the amplitude is varying. Another method is frequency modulation, where the actual frequency of the waveform is varied in step with the audio modulation. And so modulation is adding information to be carried by a radio frequency signal. And here's a block diagram of an old broadcast AM transmitter where they'd have a crystal-controlled master oscillator, driver buffer amplifiers, a very high-powered output RF deck, and an equally high-powered audio amplifier inside to impose modulation to go out to the antenna. So those are some very simple, basic transmitters, block diagrams. Receivers. Receivers are interesting because, well, they got a lot of knobs and dials, and I love them. The superheterodyne receiver was the most common type in the past. And the superheterodyne receiver had radio frequency energy coming in from an antenna. It would go into something called a mixer stage. And in the mixer stage, you would have another input called the oscillator. We've talked about oscillators generating a single frequency. And in this mixer, the two incoming frequency and the oscillator frequency would mix. We'll talk more about that. It would come out, and one of the outputs would be at an intermediate frequency that we would desire. We would filter that, amplify it, and then send it to a detector of some kind or a demodulator, and then out to an amplifier and out to a speaker. The mixer stage, that's this stage right here, looks like this in a schematic, where you have the RF coming in this case from the antenna, the local oscillator, and then the output. The output of a mixer is the input frequency plus this input frequency, the sum, or the difference between whatever is higher minus the one that is lower. So in a mixer, you have four things coming out of a mixer: the original signal, the local oscillator signal, a sum signal, and a difference signal. We use mixers to change frequencies. We filter out after the mixer the one frequency that we want. So typically it's this one, or the sum, or the difference. Either of these is the one that we want. We've changed the frequency of the original signal to a new frequency that we can amplify and use to our purposes. So here's for example, a block diagram. I think it's of an FM, could be AM radio. Signals coming in through a radio frequency filter, through an amplifier, our mixer, to change that frequency down to an intermediate frequency that we desire. Very common was 455 kilohertz. Then a demodulator of some type to change that RF energy to audio, and then out to our speaker. All right, last questions. Which of the following is used to convert a signal from one frequency to another?
Bravo.
That's a mixer. That's in the receiver. Although we have mixers and transmitters too. What is the name of a circuit that generates a signal at a specific frequency?
Delta.
That's an oscillator.
Delta.
Yeah. And which of the following describes combining speech with an RF carrier?
Charlie.
Modulation. And that, ladies and gentlemen, is the end of Chapter 3. You made it. Are there any comments or questions before we get out of here? Let me, on the Zoom class, let me remove the spotlight so I can see you a little better.
Can I ask you a question? One of the schematics, there was the transistor, it had like letters, 3 different letters at different points. I was just wondering what those meant.
Okay, well, it could have been the base collector or emitter, BCE, or was it NPN or PNP?
It was, I think it had the B on there. It was like on one of the schematics.
Right. So base collector emitter, those are the 3 legs
Okay.
of a bipolar transistor. And there are different circuits configurations. Generally, the base is considered to be the input of the device, but yeah, that's a bipolar transistor, base collector and emitter.
Bipolar.
Yeah,
Okay. Thank you.
you bet. Any other questions? Thank you very much for your attention tonight. You've done great. Chapter 4 is next week. Read that and watch for an email from me tomorrow with a follow-up to this class. Until then, 73, y'all.
Thing 73.
See you next week.